So let's refresh our memory about what we've covered and what we've learned so far. We talked about system optimal and how to formulate it as an optimization problem. The objective function in the system optimal assignment was that we want to minimize the total system travel time, or TSTT, right? So this is total system travel time. Total system travel time. And total system travel time is basically you multiply the link volumes. So this is link volumes by the travel time of the link. So this is link travel time. And you sum it over all the link, summation over all links in the network, and that gives you the total system travel time. And we want to minimize this. So it's a minimization problem. We want to minimize the total system travel time, subject to a set of constraints. What constraints? The non-negativity constraint, the linear equality constraint. So this non-negativity was this was path flows must be non-negative. Also, the linear equality constraint was about conservation, demand conservation, right? Demand conservation. And the first one is actually the relationship between link flow. So this is link flow and path flows, right? So this was path flow. Path flow. And this was the link path incidence matrix, a 0 and 1 variable that tells us whether a link belongs to a path. And then it's a multiple summation over all ODs, summation over all paths, summation over all the destinations, summation over all the origins. So for all the origin and destinations and all the possible passes between all these origin and destination, you sum all these path flows, and then you get all the link volumes or all the link flows. So this was system optimal optimization problem. And as we talked before, let me just highlight this, which was also in the quiz, I guess. One of the quizzes, I'm not sure, was it last week or the week before? If you look, the objective function is stated in terms of link flows, while the constraints are stated in terms of path flows. So that's an interesting distinguish that we make, and I want you to bear that in mind. Same thing applies to the user equilibrium optimization problem, where the objective function is stated as a function of link flows. So this is link flow, while the constraint are all stated as path flows. You see all these path flows. Again, a non-negativity constraint, demand conservation, linear equality constraint, and also the relationship between path flows and link flows. But then one big difference, so the constraints are the same here in terms in user equilibrium versus system optimal, but it is the difference between system optimal and user equilibrium is in this objective function, where we want to minimize each individual travel time. But how can we get that each individual travel time? This is called Beckman function, if you remember. So this is called Beckman function, which physically represents the area underneath the link travel time function. So if this is T and this is X, and this is the link performance function from 0 to XA, if we sum, this is the summation over all links. So sum over all links in the network. If we sum over all the links and if we get this area underneath the travel time function. That is equivalent to the Wardrop's principle, saying that each individual will selfishly try to minimize his or her own travel time going from any A to B in the network. So that's the objective function. What else I have here? I think we covered this. So same as system optimal as we talked before. Let me see if there is any question. I think I heard a beep from the chat box. Yes. Why is the U optimization is not a function of link flows? The UE optimization, the user equilibrium, the objective function, it is. So look, the objective function, so your question is actually not correct. The objective function includes link flow. So this is link flow, and this is link travel time. But the constraints have the path volumes. Same thing with the system optimal, that we have the link volumes in the objective function, and we have path volumes in the constraints. But I think if you remember from the quiz was specifically, in the one question in the quiz was specifically asking about the optimality conditions, not necessarily the objective function in the user equilibrium optimization problem. So if you look at the UE optimality conditions that we derived last week from the general optimality conditions, like trying to put together the Lagrangian function, taking its derivative, etc., etc. If you look at the optimality conditions, you can see the optimality conditions for the UE is actually all based on the path flows. And again, why is it like this? I mean, it's not something that we designed to be like this. It's, you know, when you try to derive it, when you try to get the Lagrangian function, etc., that's how it emerges. That's how it naturally comes out of the user equilibrium problem. And we talk a little bit more about path flows and link flows towards the end of this lecture. Some of the issues and questions around uniqueness of path flows, uniqueness of link flows, link-based user equilibrium solutions, and path-based user equilibrium solutions. So hopefully towards the end of this lecture, hopefully doing the workshops tomorrow, I believe, you'll have a better understanding of the distinguish between link-based and path-based optimization, path-based solution methods. But going back to this, but going back to what I was talking about, so again, yes, user equilibrium optimization and system optimal optimization problem, the objective functions includes link flows, the constraints includes path flows, but when it comes to optimality conditions, the optimality conditions is only specified as path flows. There is no link flow in this optimality conditions. And again, we talked about the physical interpretation of each of these optimality conditions, which I won't repeat. I recommend you to have a look at the previous lecture. And that's a table that we put together from last week. So on the left, this was the general optimality conditions for any optimization with more than one decision variable and a non-negativity constraint and a linear equality constraint. And using the Beckman function, we did derive this user equilibrium assignment optimality conditions. And it's just an equivalent of this. So it's just putting them into a nice table summary format. But now the question is, how do we actually solve this user equilibrium problem? We talked about many different algorithms. If you remember, we talked about incremental loading. We talked about algebraic solution, where you could use simultaneous equations to solve the problem. But the problem with simultaneous equations and also either graphically solve the user equilibrium, or also the incremental loading, is that if the network gets large, or if the travel time function is slightly difficult to work with, mainly if the network gets large, it's really hard to write tens of thousands of simultaneous equations to try to solve. And therefore, iterative heuristic solutions come into place where it helps with solving large problems. We can actually code them. We can actually write these solution methods into a piece of MATLAB code or Python code or any other language that you're comfortable with, and then you can actually solve large networks with it. So that relates to being scalable. So the methods we really need to solve in reality, in real world, has to be scalable because the problems in the real world are large. They're not really limited to the kind of problems we solve in this class, like having one OD and only 2 or 3 passes. In real world, the problems are really large. So we really need some scalable methods. I think we touched on this iterative framework last week, where we start with calculating path travel times, and then we find the shortest path using a Dijkstra algorithm or any other shortest path finding algorithm. And then we adjust path choices. We shift volumes from one path to another path in a smart way until we reach equilibrium. And then we do this in an iterative manner. So there are different methods of user equilibrium. In the first part of the lecture today, we're going to talk about 2 methods, which is the MSA method and Frank-Wolf method. These 2 are link-based methods, and the other 2, actually the other 3, are path-based methods. So the other 3 are path-based methods. You're going to see in a little bit that what do I mean by link-based versus path-based. The first 2 that are link-based, method of successive averages and Frank-Wolf algorithm, are commonly used. They've been around for many decades. One problem with them is they are usually slow in convergence, so it takes a very long time and many iterations to reach convergence on large networks, while path-based methods like the gradient projection or algorithm B or traffic assignment by paired alternative segments, or known as TAPAS, are relatively faster and they can reach convergence much quicker than link-based approaches. But there is pros and cons with each of them that we'll cover. So let's have a look at an example here, which we have a very simple small network from origin 1 to 2. We have 2 links or 2 paths. 50 vehicles are going from 1 to 2. And at the equilibrium, 30 travelers will end up choosing the top route and 20 travelers the bottom route. And that leads to the equal travel time between the 2 paths. Gives us 40 minutes. So if you really want to solve this problem of user equilibrium with some of the methods that we've already covered, like the incremental loading, or for example, assigning everybody to the shortest path first and then shifting them one by one to the other path until we reach equilibrium, that will be very, very slow and tedious process. And it takes a very long time to reach convergence, as I said before. But the main question that we try to answer with some of the existing solution methods is we actually need to shift a fraction of the users each iteration. So from one iteration to another iteration, we need to understand and we need to smartly find a way to shift the right amount of people from one path to another path. So in relatively a small number of iterations, we can manage to spread them and reach the equilibrium point where the path travel times become equal. But trying to smartly find that fraction, what fraction of people should I switch from one route to the other route, that's the main problem that many different methods try to solve differently. So the general framework here is that you start with some feasible link flow solution. You calculate link travel times, and then you find the shortest paths between all origin and destination. And then F star is defined as an assignment of the demand to the shortest path only. And when you assign the demand to the shortest path from each origin destination, then you actually get X star, which is the link volume. So this is F star is the path volume, and X star is the link volume on the shortest path, okay? So this is link volume on the shortest path. And again, we know there is a relationship between link flows and path flows, as we talked before. And then that's where the tricky part comes in, where different methods do it differently. That's for we need to choose a lambda value between 0 and 1, and then try to update the link flows in the next iteration as a function of the link flows in the previous iteration and the link flows on the shortest path and this lambda value that we have to magically find. And that is basically, and this is step 5 is the key in the iterative framework. So look, again, I talk about it again. I mean, we're going to see it in an example, so don't worry if you don't get it fully now. So this X prime is going to be the link volume of the next iteration is equal to that lambda value that we have to magically find multiplied by the volume of the link if we assign everything to the shortest path, plus 1 minus lambda multiplied by the X flows, the link volumes of the current iteration. So this is current iteration, X prime is the next iteration, and X star is the link volumes associated to if we assign all the demand to the shortest path. And this lambda value, we have to find it. And then if we do this reiteratively, if we get close to the equilibrium, we can stop. Otherwise, we have to continue and repeat this. But there are two things in this algorithm that should look a little bit fuzzy to you, as I talked about, I guess. And that is, how should we choose this lambda value? And what does it mean to be close enough to equilibrium? How do we define close enough to equilibrium? So how do we choose lambda? Choosing the lambda depends on the solution method we use or we're going to work with. As I said, different methods do it differently when it comes to calculating lambda. So there are ways to go wrong. If lambda is too big, that means we are actually overcorrecting, meaning that we shift a lot of people from one path to another. And that actually causes a slow convergence. And if we also, it means you actually fluctuate or oscillate a lot between one iteration to another iteration. So you shift a lot of people from one path to another, and then in the next iteration, you find that, ooh, you overcorrected. So you shift back a lot of people back to the initial path, and then this creates some oscillations. And if you also go with a very, very small lambda value, that means it looks like an incremental loading, that it will take a long time to finish. Imagine you only take one person from one path to another, put it into another path. And then if you do it just one by one, it takes ages to finish. And the other problem was but the other tricky thing in the iterative framework is that how do we know we're close enough to the equilibrium? And that means we actually need to define a stopping criteria, just like all the previous algorithms we had. We can introduce like something called a relative gap, or we can look at the some kind of another measure that we can define to find out whether we are close to equilibrium. So the termination criteria is usually found is usually based on, as I said, a relative gap measure that we've worked with, or sometimes by looking at the second one, which we say, if for example, if this is my link volume and this is iteration, for example, iteration 1, 2, 3, and so on. For example, in the first iteration, this is my link volume, then it goes all the way down, up, down, up, down, up, down. And then over time, we can see that the link flows do not really change much after some iterations. And that is a suggestion, an indication of reaching equilibrium, because the more you go, you don't really change much of the link volumes. So that could be a measure that can capture this a smooth pattern or lack of like large fluctuations could give you an indication of that's where you need to stop the algorithm, for example. Again, speaking of termination criteria, it's always best to measure convergence based on consistency with the equilibrium condition. And that means maybe that means we should probably rely on like some of the measures we've been already working with, like total system travel time, and something new probably to you is the shortest path travel time. So these TSTT that we already know what it is, and this shortest path travel time. So we already know how to calculate shortest path travel, total system travel time. So total system travel time was the link volume. So this is the link volume multiplied by the link travel time. So this is link volume and this is link travel time. Summation over all the links. That gives me the total system travel time. But what is this SPTT, the shortest path travel time? So shortest path travel time looks similar. The function looks similar to total system travel time, but the only difference is this X star here. And this is the X star is that if we assign all the demand to the shortest path, this X star represents that scenario, and it gives me the link volumes if all the demand was only assigned to the shortest passes. So we have the X stars, we have the travel times, and then we multiply it to each other, and then we calculate the shortest pass total travel time. Again, we're going to see that in example how it gets calculated, okay? So just bear with me for a second, for a minute or two, and then we'll get to an example. And then, I mean, shortest pass travel time can also be written as a function of this kappa that we had before, dual variable we had in the Lagrangian function, but we don't have to worry about it now. And added one key point here that you need to take away is that at equilibrium, at the equilibrium point or at an equilibrium solution, TSTT is equal to the shortest path travel time, right? Because again, at the equilibrium, we said people have minimized their travel time. So that means if we are at the equilibrium point, everyone in the network is happy about their routes. That means they have taken or found the shortest path for themselves. So that basically means TSTT, the total system travel time, must be equal to the shortest path travel time. So if at the equilibrium TSTT is equal to shortest path TT or SPTT, that means if we are close enough to equilibrium, to find out how far, let me put it this way, to find out how far we are to the equilibrium, what we can do is we can actually look at the difference between the shortest path and the TSTT. So if the TSTT, the total system travel time, is very, very large, much larger than the shortest path total travel time, that's an indication that you are very far from equilibrium. So, and that's a very nice lead here to try to find a gap, try to define a gap measure that can actually quantify this difference between the TSTT and the shortest path travel time. And that's what leads to the definition of this relative gap that we use as the stopping criteria in the algorithm. And that is a very commonly used gap measure, which looks at the total system travel time over the shortest path travel time minus 1. So at the equilibrium, we said that TSTT is equal to the shortest path travel time. So at the equilibrium, this is 1. So that means 1 minus 1, it gives me a gap of 0. So if you reach a gap value of 0, that means we are exactly at the equilibrium point. But because this is a heuristic method and we don't necessarily, I mean, it may take very, very long time to reach the exact equilibrium point. But if we are happy with being close enough to the equilibrium, that means if the gap is really small, let's say, I don't know, 0.001 or, you know, like some small numbers that we can tolerate or we can accept, we can stop the algorithm and say that we're happy with the solution that's close enough to the equilibrium point. There is another measure that we can calculate based on this TSTT and SPTT, and that is called average excess cost. This average excess cost, or AEC, is also a function of TSTT and shortest path travel time. So we subtract shortest path travel time. So it's TSTT minus SPTT divided by what? Divided by the total demand in the network. So this is summation of the demand, summation of all the demands over all the origin and destination. R was the origin, if you remember, and S was the destination, right? So summation over all the ODs, you sum all the demand across all the ODs, and then you calculate the average excess cost. This is known as a normalized gap, which shows how much longer the average vehicle's trip is than the shortest path available. So again, at the equilibrium, this ratio, this AEC, should be equal to 0. If we are close to the equilibrium and we are happy about that, we can just stop the algorithm if this AEC is a very small number. But going back to that lambda value, like what fraction of people should we switch from one to the other path? We talked about that we don't want to choose a very large lambda because it oscillates, it creates some oscillation between volumes from one iteration to another, and we don't want to go very small because it takes a very long time. And that leads to these two methods. One is called method of successive averages. That's a very commonly used method in the literature. So if you want to apply a very simple method, MSA is the best. Frank-Wolf is a little bit more complicated, but it has the advantage of being a little bit more quicker in terms of convergence. It's still very slow on large networks, but it is faster than MSA, okay? And MSA also requires a lot of computer memory. So if you don't have enough RAM on your computer, MSA may not really work. And as I said, it's really slow. I mean, I have a nice word here. It says glacially slow. So now let's start with going over the method of successive averages, or MSA. So how does MSA work? So once we found the shortest path between any origin and destination, how do we decide how many travelers to shift from one path to another, and how many should stay on the current path? So what is behind this MSA theory? How does MSA work? So we initially shift a lot of travelers, but as the algorithm progresses, we shift fewer and fewer until we sit down on an average. So the lambda value that we're going to use is basically 1 over the iteration number. So this lambda I would be 1 over the iteration number. So if you're at iteration 1, lambda is 1. That means you do an all or nothing assignment. At iteration 2, lambda would be 1 over 2. Iteration 3, lambda would be 1 over 3rd. Iteration 4, it would be 1 over 4. And you can see that, imagine if we go 10 iterations, lambda at iteration 10 would be 1 over 10. So you see, as we progress in the algorithm, as the number of iterations increases, that lambda value becomes smaller and smaller, meaning that we shift fewer and fewer people. This method definitely converges because of how it's designed, but it takes a very long time, as I said before. So one advantage of MSA is that you never need to work with the path flows. So it is simply just based on link flows, as we're going to see in a minute. And the algorithm operates entirely in the space of link flows. So we don't really care about path flows here, and we just work with the link flows and we reach a convergence point. So let's see what the steps are in the MSA, and then we go over an example. So we first start with iteration number 1. We find the shortest path between each origin and destination, and we calculate the relative gap. Unless it's first iteration. In the first iteration, we don't need to calculate relative gap because there's no relative gap calculation. It's the first iteration. But in a step 2, when it comes to iteration 2, 3, or 4, we calculate the relative gap to know when we should stop. So the way it works is we shift travelers to the shortest path. So we first find the link flows. If everybody were traveling on the shortest path found in step 2, and we store that in something called X star. Again, you remember I told you X star is defined as the link flows if everybody was traveling on the shortest path. If this is the first iteration of course, the volumes would be equal to that x star because we don't really have any lambda, or lambda is equal to 1. But if we are in iteration 2 or 3, imagine we were in iteration, so this is lambda, right? So lambda is 1 over I. If we are in iteration 2, 3, or 4, and so on, the new link volumes that we have to calculate is basically lambda multiplied by x star plus 1 minus lambda multiplied by xi minus 1. And that is the volumes from the previous iteration, right? And then with this formula, with this simple formula, which is a function of this lambda value, we can calculate how much flow should I shift from one path to another path. And then when we shift some people, we recalculate the link travel times, we calculate the relative gap. If the stopping criteria is met, we stop. If not, we go to the next iteration and then we continue this iterative framework. But to better understand this, let's actually have a look at an example. I guess you won't really understand the MSA unless you really do an example here. Let me see, what time is it? Okay, we still have time. So let's have a look at this easy example with two links or two paths and one origin and destination. There are 10 travelers want to go from A to B, and we have the link performance function on each of the links. So we first do an initialization, meaning that we begin by taking free flow cost. This is the cost that no one is on any of the links. So the network is empty. So what would be the shortest path from A to B when the network is empty? X is 0, X is 0, no one is in the network. So this would be the shortest path. So the top path would be the shortest path in this case, right? And that is called initialization. So the top path is the shortest path because network is empty, and that travel time is 1, the other one is 10. So this is 1 is smaller than 10. So everybody will take that. So that's the free flow cost. So what we do is we do an all or nothing assignment. So we assign, or AON, we assign everybody to the shortest path. So that means everybody will take this spot, will take this top path. So path 1 is shortest, so all or nothing flow assignment. So that means x prime 1 is 10 and x prime 2 is 0. So this is link 1. And this is link 2, okay? So x1 is equal to 10, x2 is equal to 0. And, or in another way, if you want to write it in a matrix format, we can actually write it as x all or nothing equal to 10, 0, okay? So that's the result of an all or nothing assignment when we work with at iteration 1, when there's nobody in the network. So people find the first link or first path as the shortest, and they take it. Now we have some volumes on the links, right? So we can actually update the link travel costs, right? So let me hide this. So we can actually update link travel costs now based on these flows. So let's actually update the link travel costs. So now that we know we have 10, so this would be 10 power 2, this would be still 0. So the new link costs would be 101 and 10, right? So this x1 becomes the old flow vector, and now the goal is how can we find x2, right? x2 in terms of, sorry, superscript, not subscript. x2 meaning that the volumes on second iteration. The volumes in the second iteration. How can we find the volumes in the second iteration? And we had a formula for it, right? So the formula we had was a lambda x star plus 1 minus lambda x1, right? So now let's have a look. Before we use this formula, let's have a look which one is now the shortest path. So now that we've updated the link costs, we can see that the bottom path is the shortest path, or path 2 is cheaper. Now we do another all or nothing assignment, okay, to calculate this XAON or X star, okay? This is also X star. So that means everybody now, if we want to assign all or nothing, if everybody was going to take the shortest path, everybody would take the second path, right? So it would be X star 1 would be 0, X star 2 would be 10. And we could write it in a matrix format like this, right? So everybody would take the second path. But now the question is, when we want to get that second iteration volumes, we need how much people should we shift from one path to the other path? And we're going to work with the MSA formula, which I just talked about. And in this case, because we are at iteration 2, lambda is actually over 1. Lambda is actually 1 over 2, meaning that you can switch half of the people from one route to the other route. So what will happen is we say now at iteration 2, we assign, we shift half of the people. So it would be, so the new, so I would say x1 subscript is the link. So this is iteration. So iteration 2 link volume 1, iteration 2 link volume 2. Okay, so what would be x21 and x22? So again, this 2 is the iteration, this 1 is the link number, okay? Link number. So that would be, the lambda is 1.1 over 2, multiplied by the all or nothing assignment that we did. Remember, all or nothing assignment was, because now the shortest path is this one, nobody's going to use the top path. So top x1 all or nothing would be 0. Sorry. This would be 0 plus 1 minus lambda multiplied by the original x11, the volumes from the previous iteration. And the volumes from the previous iteration was 10, right? Because initially everybody was taking the top path. So it's 10. And if we do the same thing for the other link, it would be half of the now all or nothing volume. The all or nothing volume is 10 plus half of the x21. What was the volume from the previous iteration? This was 0, right? So if we do this, we actually find that we switch half of the people from one path to the other path, right? So it would be now 5 and 5. So it would be 5 versus 5. Now we can recalculate the costs based on the new flows we have, right? So if we now calculate the new, so this would be 5 power 2, the new cost would be 5 power 2. We calculate 26 versus 35. And then this was the outcome of the link volumes from iteration 2, right? Now let's do another all or nothing assignment to get that X star or the X all or nothing assignment, okay? So X star or X all or nothing assignment is the same as I'm talking about here. I interchangeably use that. So if we do all or nothing assignment with the new cost, everybody will choose the top path, right? So the all or nothing assignment would be 10, 0. So everybody will choose 10. Nobody used this one. 0. Everybody, 10 people choose the top path. 0 people will choose the bottom path. And now if we use again the MSA formula, now the goal is to get the x31 and x32, right? The volume of the link 1 in iteration 3, the volume of link 2 in iteration 3, which is lambda x star plus 1 minus lambda x21 and lambda x star plus 1 minus lambda x22. And again, this would be x star 1, x star 2. So what is lambda now? Lambda is, we said it's 1 over I, right? I is the number of iterations. So we are now in iteration 3, so lambda would be 1 over 3. So if you put it in the equation here, it would be 1 minus 1 over 3 what is the all or nothing assignment for the first path? It would be 10, right? Because this is now the shortest path. 10 people will use this. So this would be 10. 1 minus lambda is 1 minus 1 over third, so it's 2/3. And then what was the volume of link 1 from the previous iteration? It was 5, right? So we have 5 here. And now if we do the same thing for the second link, we find that it's 1/3 over 0. So the x all or nothing on the second link would be 0 plus 2/3 multiply the volume from the previous iteration, which was also 5. And now the new link volumes would be 6.6, 6.6, and 3.3. And now that we have new volumes, we can actually recalculate the costs, right? So if we recalculate the costs, so this was 6.6 power 2, this is actually 3.3 power 2. So if you recalculate the costs, we can see that now the shortest path is the bottom one. So let's redo this again. So we do an all or nothing assignment. That means 10 people will do here, 0 will do here. So this is x star, and this was the x31 and x32, right? So x star 1 and x star 2. And now we are at iteration 4, so lambda would be 1 over 4. So again, if we use the MSA formula, it would be 1 over 4. So for example, have a look at this one. 1 over 4 multiplied by the x star of 1. What is x star of 1? 0. Plus 1 minus 1 over 4 multiplied by the x1 from the previous iteration, which was 6.6. So now if you put it into the, if you put all these numbers into the equation and do the same thing for x2, we actually get to 5.5 again. So now the volumes would be, again, 5.5, right? So now that we have this new the volumes at iteration 4, we can recalculate the shortest path, right? We can recalculate the path cost. So now it is 5 power. So this is now iteration 5 power 2, and it would be 2635. And then we do another all or nothing assignment. This is the top path. This is the bottom path. Let's do the all or nothing assignment. So x star 1 would be 10. X star 2 would be 0, right? This was from the previous iteration, the x values, and now we want to find x51 and x52, right? So which is lambda multiplied by x star 1 plus 1 minus lambda x41, which is the volume of link 1 in iteration 4. And same thing for the other link, x2 plus 1 minus lambda x42. Okay? And if we use this MSA formula, and what would be lambda now? Lambda is 1 over 5 now because it is iteration 5. If we do this and we put it into MSA formula, we actually find that we'll get the link volume 6 and 4. And now if we redo this again, let's do this for another iteration. So this is now x5. If we do this for another iteration, again, we go back to 5 and 5. So this is now x6. Let's do that. If we continue doing that, for iteration 7, 8, 9, and 10. And at iteration 10, we actually see that the path costs are getting close, you see? And remember, this is what we want to see at the equilibrium. At the equilibrium, we want to see the path costs are equal for the same OD, right? For any OD, if the paths are being used, they must have equal travel time. And we see we're getting there, but not quite there, but it's close though, okay? But probably if we continue another 10 or 5 iterations, we may reach to a point where we have very, very close path costs, okay? But the question is it converged? I mean, maybe we need to calculate the gap, right? Because we don't necessarily know, is this close enough to the equilibrium point or not? And that's where we need to calculate the gap or average excessive cost or AEC in each iteration. So I'm not going to go back and calculate the gap, but I'm going to go over another example and calculate the AEC and relative gap in another example of MSA. So you also get to see application of MSA on a larger network and also calculation of the relative gap and AEC here. But before I continue, any question from the previous example? I hope I wasn't too fast, or I hope it was clear enough. So if I go back to the chat box, if there is any question, okay, there was a question before. What does the integration of the Beckman function about? John Yuan, I talked about this in the last lecture, so please watch that lecture. We talked about Beckman function and then what does integration supposed to mean. And if you also Google Beckman function and traffic assignment, you'll find plenty of answers for that. A bit confused about the constraints in the Beckman function. Again, sorry, this is from, I was just refreshing our memory from last week lecture, so I'm not going to go back. These are questions related to the previous lecture, and I think we talked about it in the previous lecture. So please go back to the last week's slides and last week lecture. Hopefully you'll find the answers. If you were still confused, please post your question on Moodle. And we'll be happy to help. Stephen, you're asking about X. Yes, X star is the same as X all or nothing assignment. Yes, in the MSA formula, X star. So if I go back to the slides, yes, X star, as I said, so this X all or nothing assignment. And again, remember that it was, let's say Xn is equal to lambda X star or X all or nothing assignment plus 1 minus lambda Xn minus 1. This is MSA formula. And yes, this X star, you can use X all or nothing assignments. And that's what we do here. I mean, this is the step 2 here, that at every iteration, we find the shortest path, we assign everybody to the shortest path, we find this X star, and then we use this X star or X all or nothing assignment in the MSA formula to actually calculate this Xn at every iteration. Any other question? I have another example which is more interesting to look at. Okay, let's have a look at the second example and then we'll continue from there, okay? So now let's have a look at a larger example. Let me see, what time is it? Okay, we still have time, so hopefully we can finish this example and then we'll take a lunch break, okay? So this is a larger network. This is, I have 7 links in the network. I have 2 ODs, 1 to 3, and 2 to 4. So this is my demand matrix. And we can see for going from 1 to 3, there are 2 possible paths. So let me choose a different color maybe. So there is one path here. So let's call that path 1, 3. And there's also another path here on the bottom, which is the second path, which is 1, 5, 6, 3. For the other OD, which is 2 to 4, right? Also one path here, which is 2, 4, and there's also another path here, which is 2, 5, 4. This 2, 5, 6, 4 is the nodes, right? So 2, 5, 6, 4. So we have 2 paths available for each OD pair, and the link performance function is given, and that is 10 plus x over 100 for all the links. For all the links have the same identical link performance function. Okay. Now let's start with the MSA implementation. So we start with initialization. We set the iteration number equal to 1. So iteration is equal to 1. We find the shortest path when there's no traveler on the network. Remember, we have the link performance function. So that means if x is 0, this is 0. So all the links will have cost of 10, right? But we need to find the path travel time here, right? Because it's shortest path, not necessarily shortest link, right? So we use the travel time on links, the free flow cost. So link free flow cost to find the shortest path. So in the network, the first two was for going 1 to 2, and the second two paths was going from, this was 1 to 3, going from node 1 to 3, and this was going from node 2 to 4. Okay, so we had two passes for each of the ODs. And if we calculate the shortest path, again, let's have a look at the network here. Let me erase this things that I've written. So when the network is empty, this is 10, this is the cost 10, cost 10, cost 10. So obviously this path will have a cost of 10, and this path will have a cost of 30, right? Because it has 10 plus 10 plus 10. So we'll have a cost of 10 for this path, 30 for the other path, and if you do the same thing for the other two paths for the other OD, you'll get 30 and 10. And which ones are the shortest passes? So for each OD, we do it separately, right? So remember, we do this for every OD separately. So for the first OD, this path would be the shortest path, and for the other OD, this path would be the shortest path, okay? So now we know what the shortest passes are. And now we do an all or nothing assignment, and let's put it in a matrix format, right? So we don't have to write x star 1, x star 2, and so on. We put it in the matrix format, it's easier to deal with. So it would be, I want to write it now here so you know. So this would be x star 1. So these are all the link volumes now, right? So these are all the link volumes. And this would be x star 1, 2, 3, 4, 5, 6, 7. Whatever that 7 is. So if I go back to the previous slide, if we do all or nothing assignment with the shortest passes, this would be x1 and this would be x7, right? So for this OD and these paths, everybody will go with this path, 5,000, right? All the 5,000 that was supposed to go from 1 to 3 takes this path. And for the other one, everybody will take x7. So x7 would be equal to 10,000, right? Because that's the shortest path going from 2 to 4. So going back to this, so we write the x star, so we're going to use that, right? Because it is iteration 1, x1 is equal to x star. Basically means that lambda is equal to 1. Again, remember the MSA formula. MSA formula says lambda x star plus 1 minus lambda x n minus 1. So in this case, it would be x0. We don't really have anything in the previous iteration. This is iteration 1. So if lambda is equal to 1, this entirely goes away. It's 0. So we end with x1 is equal to x0. That's where it comes from. It still uses the MSA formula, but because this is first iteration, we don't really need to use the MSA formula. We can just say x1 is equal to x star. So if x1 is equal to x star, that means we can actually get the new travel times. So if we calculate the new travel times, on the links, if I go back, so remember this was the link performance function. So what would be T1? Oops, sorry. So T1 would be equal to 10 plus x1 over 100. So x1 is 5,000. So this is 5,000. So this gives me 10 plus 50. So it's 60. So the travel time of link 1 would be 60. Nobody's using link 2, 3, 4, 5, and 6. So the travel times remains 10 as the shortest path in the shortest when the network was empty. And x7, if we do it similarly, we know what x7 is. x7 is 10,000. So we can calculate T7 using the link performance function, right? So if you calculate T7, you get this 110. And now we find the new shortest path. Now the costs on the links are updated. We can find the new shortest path, right? And then we can check if we're not converged, we go to the second iteration and then we adjust path flows, right? So let's now look at that. So these are the new link costs, right? So these are the new link costs that we updated from the from the volumes, and then we can find the new shortest paths. So it's easier to write it in a table like this. So if these are the new path travel times, we can see that now for the first OD, this would be the shortest path. It's 30 is smaller than 60. And for the other OD, 30 is smaller than 110. So this is now the shortest path. So what we can do is we can actually now do an all or nothing assignment, right? I mean, before doing that, we can actually let's calculate AEC and the relative gap as we talked before, okay? Then we continue with doing the all or nothing assignment at the beginning of the iteration too. So let's calculate AEC. What was the formula for AEC? It was the difference between the total system travel time minus the shortest path travel time divided by the total demand. So divided by the total demand is obviously 5,000 plus 10,000. We had it from the OD matrix. What is TSTT? Remember, TSTT was total system travel time, which is it was the summation of overall XA multiplied by TA, right? So it's basically 5,000 multiplied by 60 plus 0 multiplied by 10 plus 0 multiplied by 10 and so on and so forth until 10,000 multiplied by 110, because this is XA, this is TA, right? So I'm calculating this summation of XATA, which gives me this TSTT here. So I can easily get TSTT. But how can I calculate this SPTT? How can I calculate this SPTT? What was the formula for SPTT? The SPTT formula was, summation of TAXA multiplied by X star A. So that means if we assign everybody to the shortest path, and then we use that volume multiplied by the travel times. So that means, for example, if I go back to the table that we found, we calculated. So this is now the shortest path, right? So I have this path as the shortest path, as the shortest path, and each of them have a travel time of 30. That means this is now the shortest path. This is also now the shortest path, right? And if I do an all or nothing assignment, that means 10,000 will use this path and 5,000 will use this path, right? So now what I can do is I will multiply the that would be the new cost, right? That would be the new path cost. So it would be, let me go back to the original SPTT formula just to make sure we're working with the right formula here. SPTT, where is SPTT? Yes, okay. So it's X star is the assignment of all vehicles to the shortest path using the travel time Tij, okay? So if I go back to this example that we are solving, so we are trying to calculate that SPTT, right? So SPTT now would be the X all or nothing assignment multiply. So now with the new travel times, the shortest path is this new path and also this one. So the new shortest path cost is 30. So what we end up doing is we end up multiplying this 5,000 by this shortest path cost. So this is these two are the new shortest path cost, right? Using the all or nothing assignment volumes. So it's just using the all or nothing assignment volumes. So it would be 5,000 multiplied by 30 plus 10,000 multiplied by 30, because this is the new cost of the all or nothing assignment. And then if you calculate this AEC, if you calculate this ratio, you get a relatively large number. You remember we said at the equilibrium AEC is equal to 0. But this is very far from 0. That means we should continue another iteration. So let's calculate another iteration. We recalculate SPTT in another iteration as well. Okay, so if you didn't really fully get how we calculate AEC, we're going to see again. So that means AEC is still large. So let's do another iteration. So let's do iteration 2. So we already calculated that this is now the shortest pass for the first OD, and for the second OD, this is the shortest pass. So we do an all or nothing assignment. That means everybody will take this path and everybody will take this path. And as a result, we get this X star 1, X star 2. So why this is 15,000? If I go back to the original network, let me do it here. Remember, we now said this is now the shortest pass of this OD. This is now the shortest pass of the OD. So 5,000 people will take this pass. So it would be 5,000 in this link and 5,000 in this link. And 10,000 will use the other path. So that would be 10,000 here, an additional 10,000 on this link, and then 10,000 on this link. So that gives me the volume of this link tree to be equal to 15,000. Okay, while this remains 10,000, 5,000, 5,000, 10,000, but this one in the middle, the link volume be 15,000, 5,000 of them relates to the demand going from 1 to 3, and 10,000 relates to the demand going from 2 to 4. So that's where the 15,000 comes from. I just want to tell you where this 15,000 comes from, okay? And so this would be my X star. Now I need to use the MSA formula. So lambda is equal to 1 over I, so it would be 1 over 2. So x2 would be 1 over 2 multiplied by x star plus 1 minus 1 over 2 multiplied by x1. So I already have x1 from the previous iteration. I already have x star here, right? I already have x star here. And now I can calculate x2 just using the MSA formula. So now that I have the new volumes on the links, I can recalculate and update the travel times on each link, right? Using the link performance functions that I was given. And now find the shortest path and check the convergence. So given this new travel times, if we apply Dijkstra algorithm or any other algorithm, you'll find that now this is the shortest pass. And again, this becomes again the shortest pass. So the shortest pass would be this and this. And now let's, if these are the shortest passes with the new travel times, what would be the cost of the shortest pass? We can still calculate. So because this path only has link 1, so the cost of this path is 35. And the cost of this pass is 60, right? So this is 35 and 60. This 60 comes from here. And now, if we want to calculate the AEC would be like this, where we first find the TSTT. Remember, TSTT was the summation of the XATA. So it's simply 2,500 multiplied by 35 plus 2,500 multiplied by 35 plus this multiplied by this plus this multiplied by this, and so on and so forth. So we calculate this summation of XATA. So this gives me the TSTT. So it's simple, total system travel time. The denominator is also simple. That's the total demand. So 10,000 plus 5,000. But now let's have a look at this SPTT. So the SPTT, how does it get calculated? So this 35 and 60 are the new path costs, right? So new path cost if we do all or nothing assignments. If everybody takes these two paths, that would be the costs, right? And then that means 5,000 people, 5,000 travelers multiplied by 35 plus another 10,000 multiplied by 60. So this gives me the shortest path travel time. And then TSTT multiplied by TSTT minus SPTT divided by the total demand gives me 68. Let's compare this 68 with the previous AEC. So we got 68 here, but what was the previous AEC? The previous AEC was 63.3. And now we got 68. We're actually worse, right? So we're still far from equilibrium. And again, why we're worse? If you look at AEC over number of iteration, we don't necessarily smoothly come down. it may have some fluctuations. For example, it may go up, down, go up, down, go up, down, and then finally it gets close to zero. Okay, that's why. So don't surprise if your AEC goes up in the second iteration. In the third iteration, we expect it to go down again. So if you continue doing these iterations, let me see if I have another iteration. So I leave the third iteration to you. So do the third iteration, apply the MSA, calculate the AEC. And if you do that, again, I'm going to skip some of these because I leave it to you to do this as a practice, okay? You're going to find out that, I mean, I don't have AEC here calculated, but AEC, I expect that it would be a smaller in iteration 3. As I said, it fluctuates. And then we continue this until the AEC becomes very small. And you can see in even such a very small network, it takes a very long time to converge. We are at iteration 3 and maybe 4, and we're not yet at equilibrium. And if you actually do the example, you can actually find that the AEC would be equal to 1 if after 12 iterations, it would go down to 0.1 after 64 iterations, and it will go to 0.01 after 333 iterations. So it takes 333 iterations to actually reach to such a small number. So MSA is glacially slow again.